The principle of a discounted cash flow is simple. It's a way to model the flows of money into and out of an organization, a business, an operation, or a project in such a way that takes full account of the effects of inflation and interest. Because, after all, money spent or earned today has a different value to money spent or earned in the future. So, how do we create a discounted cash flow? I'll show you. Shortly after the start of my project management career, I needed to create a lot of discounted cash flows for large multi-year projects. Today, I'm going to hit the spreadsheets again and show you the basics of how I did it. So here we are in the Excel spreadsheet, and I'm not going to format things very carefully, but I do want to put a title on my spreadsheet because that's good practice, and we'll do some minimal formatting just to show that it's a title. The first thing to do in creating a discounted cash flow is tell ourselves about the years. So let's start by putting a header there for the end of year. If I give myself enough rows at the top there. So the end of year 0, that, by the way, is now. And then we're going to put 5 more years into our cash flow. That'll be enough to illustrate everything we need. Now, once we've got our years in, we can give ourselves an income at the end of year 1. And I'm going to give myself an income of $100. Let's format that as dollars. So now we've got our starting position. But the question is, what is this going to be worth in future years? Because we know that if we have some money, we can invest it. So the first piece of information we need to add is a notional interest rate. So let's put that data at the top of our spreadsheet, and I'm going to give that the symbol I for interest rate. Let's give ourselves an interest rate of 5%. So that's 0.05. But I do want to format this as an interest rate, and I know that I'm going to have some other percentages there. So let's give that a 2 decimal place percentage format. So now we know what the interest rate is. We can calculate the payments as a result of investing our $100 income in years 1 to 5. Let's do that. So our income in year 1 is equal. But before we do that, we need to know how much capital we've got. We've only shown the income. So let's put the total capital in another column. And the total capital here is, of course, equal to that. But now, at the end of the first year, we're going to get a little bit of income. And that income is equal to our total capital multiplied by our notional interest rate. And because we're going to use that same figure as we move around, let's lock that cell in with our function F4. And when we copy that to other places, it will always draw from F4. Now, one of the things I do quite like to do is to highlight in blue the cells which are entered by hand as opposed to calculated. That keeps things nice and tidy. So our total capital at the end of year 1 is going to be equal to our total capital the previous year plus our new income. And now we can start to add all of that in to future years. So we can see, as you might expect, that the interest income increases as our capital increases. So by investment, it would appear that by the end of year 5, our $100 is worth $127.63. And Albert Einstein referred to compound interest as one of the wonders of the universe. But the problem is, we also have inflation, and that erodes the value of our money. So let's put an inflation rate onto our spreadsheet. So we're going to put inflation rate. Wouldn't it be nice if we could use the symbol I, but we've already used it. So I'm going to give it a symbol that is quite often used, the symbol K. And we're going to assume that the inflation rate is 1.5%. Okay, and we'll also make that blue because we've entered that. So now we've got an inflation rate, we can calculate the effect of the inflation in each year. So let's put effective inflation in the next column. Well, we know that there is no inflation there, so the effective inflation is 0. And these are all going to be percentages with 2 decimal places. Now, it's easy to know what the effective inflation is in year 1 because we know it's going to be 1.5%. But what's the formula we're going to use for calculating it in subsequent years? Well, the answer is that the formula that we're going to use is 1 plus the inflation rate in the year before times 1 plus the annual inflation rate. Again, we use our function F4 to lock that cell, and then we need to subtract off the 1. And as we would hope, that gives us a 1.5% there, but when we copy that down to future years, we can see that the cumulative effect of inflation grows. And that now allows us to calculate the value of our capital in present terms. Let's call that today's money for the sake of argument. All we do is we take our total capital and we divide it by 1 plus our effective inflation. As you'd expect in the first year, it hasn't diminished, but as we extend that to future years, we can see that the value of our capital drops relative to the total capital that's there. So our $100, which turns into $105 by the end of year 1, is worth, in today's spending power terms, $103.45. Now I'm going to replace this header here with the correct label that we use in discounted cash flows, and this is known as the present value, or PV, of the money we have. And it's the PV of the capital. Now, we've got a notional interest rate and we've also got an inflation rate. Putting these both in one at a time takes longer than we might need to. We can actually use a single figure to represent the effect of the interest rate I and the inflation rate K. And in economic terms, that is known as the real interest rate. We say that 1 plus the real interest rate is equal to 1 plus the notional interest rate divided by 1 plus the inflation rate. Obviously, we want to subtract the 1 off, so we can calculate that by saying that is equal to 1 plus notional interest rate divided by 1 plus the inflation rate, and then we need to subtract off our 1. So the effect of an interest rate of 5% and an inflation rate of 1.5% can be accumulated into a real interest rate of 3.45%. And that's exactly what we see in row 1. At the end of year 1, we've actually got a present value of $103.45. So it's as if we've kind of multiplied that $100 by 1.0345. As project managers, we often simplify this. We recognize that with small figures, we can make the simplification, small numbers for notional interest rate and small numbers for inflation rate. We can make the simplification without losing too much accuracy. Also recognize that our notional interest rate and our inflation rate are just estimates. So we don't need to be too accurate about them. If we're too precise about them, then we forget that they're not accurate figures. So what we can actually do is create a simplified discount rate, and I'm going to call that little r. The way we calculate the simplified rate is exactly what you'd expect. It's equal to the notional interest rate minus the inflation rate. Let's put a little formatting on this table so that we can read it easily, just using the standard Excel colors and simplified formatting, and that looks fine. However, we need to create a new table to take this to the next step. Let's say that our project produces a product which generates a series of payments over future years rather than a single payment in the present year. So let's again put our end of year header here. And again, we're going to put now as year 0. And we're going to go out 5 years as we did before. And again, we're going to put our income into the next column. But this time we're going to have 0 income in the first year and then $100 in each subsequent year. Now I want to introduce an additional piece of discounted cash flow jargon. We're going to refer to those income streams as payments and give them the abbreviation PMT. Now we want to take into account inflation and interest. So we're going to calculate a present value factor which allows us to do that. And the present value factor, or the discount factor, is calculated as 1 divided by 1 plus our discount rate. And we're going to use the simplified discount rate there. We're going to use our function F4 to lock the cell, all raised to the power of the year. And this is where it becomes critical that you use the right indices for the year. The first year that you use, if it's year 0, will give you a discount factor or a present value factor of 1. And this is not currency amount, it is purely a number. In fact, let's give it an extra decimal place. As we copy it down, we would expect to see that those discount rates decrease. So we can now calculate the present value of each of those income payments by multiplying the actual payment by the present value factor. And this is currency amount. And there we can see that a payment of $100 in 1 year's time is equivalent to getting $96.62 today. A payment of $100 in 5 years' time is equivalent to getting $84.20 today if we could invest our money at 5% and suffer an inflation rate of 1.5%. So the formula we've actually used here is that the present value is equal to the payment times the discount rate, or PV factor. D, the discount rate. As I tidy this up, because we're going to create a new spreadsheet in a minute to take this further, it's worth noting that we have already created a discounted cash flow. It's not the most useful discounted cash flow because it only has incomes, it doesn't have expenditure, but we're going to do that in a minute. So what we've got here is our discounted cash flow here. Year, payments, discount factor, discounted cash flow. And you may not choose when you present your discounted cash flow to show this working, so you might grey it out or hide the cell. Now, our third table, we're going to do exactly the same thing as we did before. We're going to start with our end of year, and we're going to use 5 years to illustrate how that works. But this time, before we look at our income, we're also going to look at payments. And payments should be seen as negative if income is positive. And let's assume our project has a capital cost of $100. And because it's money coming out of our account, we're going to mark that as a negative. We've spent that by the end of year 0. By the end of year 1, we've made an income on our project of, let's say, $8. And then in future years, our income might increase. Now, this is rather good performance, but let's put in some numbers here so that at the end of year 5, we make $64. So we've actually made quite a lot of money. In fact, how much money have we made? Well, we can total that up quite easily and see that we've made $160. So on the face of it, we made $160 for a $100 investment. Sounds good, but what's the impact of inflation and interest rates? So let's build our discounted cash flow, and we start by putting in an undiscounted cash flow. And that's very easy because all we do is we add our payments to our income. And we can see that at the end of the period, we should be able to calculate our simple profit or loss. But now we need to introduce our discount factor or present value factor. To create our discounted cash flow, we need to calculate our present value. So let's have our present value for R equal to 3.5%. So our present value, if you remember, is equal to our payment times 1 divided by 1 plus R to the n. So we can just divide that by 1 plus R to the n, which is 1 plus R, and we need to lock that with our function F4 to the power of the year index. And as we'd expect, present value for the first payment is exactly the same as the actual value. And now when we copy the cells, we can see that the present values are a little bit less than the actual cash flows. And now we can do the same. We can put in our auto sum. This time we're going to column, and we can see now that the actual value of that cash flow when we have a discount rate of 3.5% is positive $40. And that positive $40 is known as the net present value. And we abbreviate that to NPV. On the face of it then, our project is a sound one. We're investing $100 and we get a net present value of $40.21. Now, of course, this figure is going to be sensitive to the discount rate. If, for example, the real inflation rate were 0, that would fall. Let's put it back to 1.5. If the notional interest rate, if we could invest that $100 at a lot higher interest, let's say we could invest it at 10%, then the net present value would start to look a little thinner. And indeed, if we had a notional interest rate of 15%, then pretty much we'd make a small loss. And therefore, it would be better to put $100 into the bank at 15% than to invest in the project. All other things being equal, which they never are, of course. So this is very sensitive to the discount rate. And we also need to ask ourselves what positive net present value is material and actually justifies the risk. Now here, we've got a return of about 40%. $40 on 100 is a very good return. But if our investment were significantly higher, let's say our payment were minus 1,000, then we'd make a loss and it would be a big one. But if our investment were not $100, but it were, let's say, $130, then one might argue that a $10 return on $130, given that we know that things go wrong and we don't always realize the gain that we're expecting, we sometimes spend more than we're expecting, that suggests that that positive net present value of $10 is not material and this wouldn't be a good project. Let's reset the payment to $100. Let's ask the question, what discount rate would render the net present value to be exactly 0? And we can do the same calculation, but we can do the present value for other R. So I'm going to use the same formula here, but I'm not going to grab the other R. We're going to use a test R. So our test discount rate, start off with 3.5 so that we know things are working. So let's rebuild our formula, but using the test discount rate. So we're going to say our present value is equal to the cash flow divided by 1 plus our new test discount rate, which we're going to lock in with our function F4, raised to the power of our year-end index. And we'll copy that down here, and we're correct. But now we can put in an alternative. Didn't spot that when I was playing around. That's a payment, so we've now got back to the same net present value. And we can do our sum here to watch that. Now, what we're trying to do is we're trying to render our net present value to 0 to work out what rate of return creates break even. So let's try 5%. That's brought it down, but nowhere near enough. Let's try 10%. That's brought it closer. Let's try 15%. That's gone too far. let's try 13%. That's pretty close. And in fact, the correct answer I know is 13.275 to within a gnat's whisker. If we can render the net present value to 0 with a particular discount rate, that discount rate is known as the internal rate of return, which we abbreviate to IRR. So the internal rate of return, in this case 13.275%, is effectively the interest rate we get of investing the $100 in this project. The conclusion is that if your project has a higher internal rate of return than any alternative investment, then your project offers you the best value use of your money, your resources, and your time. However, you must also factor in the impact of risk. And again, if your internal rate of return from your project is only marginally higher than an alternative, then if your project is riskier, you're not going to want to do that. Now, if you wanted to calculate your internal rate of return without going through trial and error, which frankly doesn't take that long, then Excel has you covered with a formula. As you might expect, that formula starts with IRR, and we need to put in the values of the cash flow, not the discounted cash flow, of the cash flow. And we need to put in a guess. Now, if you remember, my first guess was 5%. So let's use that and see what happens. 0.05. And let's see what it calculates. 13%, let's expand that out. 13.2749. 27489. So that's the precise figure. Of course, if I put in here 13.27489, then we get almost precisely 0. I don't know how many decimal places we'd need to go to expose that's not exactly 0. Maybe 5. So that's a pretty decent function. So you can calculate IRR using the IRR function on Excel. Let's do a little bit of prettifying of our table before moving on to the very last thing. Let's go back to our second table and create a couple of extra lines for ourselves. And let's put a total in here. This table shows us that under our assumed notional interest rate of 5% and our inflation rate of 1.5%, that $451.51 in present value terms is equivalent to an annual payment of $100. Therefore, the equivalent annual cost of $451.51 is $100. Now, we can calculate the equivalent annual cost, which we're going to call A, and we're going to put in an index of 5 because we're going to do it over 5 years. We calculate that by multiplying the annual payment, which in this case is 100, times what we're going to do is take the discount rate that we used. In this case, we used the simplified discount rate, R, and that's divided by 1 minus the discount factor in the 5th year, the nth year. So let's calculate that. Before we do that, let's re-expose our discount factors because we are going to use those figures. So let's do that calculation. So this is equal to 451, which is our net present value, multiplied by our simplified discount rate, which is then divided by 1 minus discount rate in year 5, and that is 100. Let's put the right format, and in fact it's precise enough that it's exactly right. So the other term you need to know is that the equivalent annual factor, or EAF, equals R divided by 1 minus the last discount rate, the last discount factor. Therefore, so AN is also equal to the PMT times the EAF.
A discounted cash flow is a powerful tool for modelling and measuring the financial impact of a project. It requires some facility with basic math and a familiarity with spreadsheets. but it is something that any project manager should be capable of creating and of evaluating. Just take some time to learn and understand the basic principles, and you're set. Please do give this video a like if you've enjoyed it or learned from it. I'll be making loads more great project management videos for you, so please do subscribe to the channel and hit the notification bell so you don't miss any of them. And I look forward to seeing you in the next one.